All right, friends, welcome to Wednesday. Today, I think, is a little bit lighter than last lesson. A little bit more straightforward, and honestly, this is some of my favorite stuff to do in physics. So this is where we left off. Blah, 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 blah. I was answering questions already, but if you still got more, ask away. Don't let that stuff fester. Energy. Is that clear? That's pretty clear, right? Take those notes down. A lot of notes on this page. Defined as the capacity to do work. An object may possess energy whether it is moving or at rest. If it's moving, it's kinetic energy. It's energy in motion. If it's at rest, it's potential energy. Yeah, say more in a bit. Is that all on the screen? Yes. Take that down. Okay, good copying. If you can't make this out, that says E sub k equals mv squared over 2. Honestly, I often write it 1/2 mv squared because this is similar to other formulas. This is just kind of the way I remember it. That's the default way I write it down. It's the exact same thing. Exact same thing. Nothing weird about it. Okay. All right, kinetic energy. It's the energy possessed by moving objects. An object in motion has kinetic energy. The higher the mass, higher the velocity, the higher the energy. Directly proportional. It's measured in joules, same as work. I think I referenced before that work and energy are almost the same thing. Page 230 illustrates how we get from work equals force times distance using essential physics equations. Essential physics equation number 4 to EK equals mv squared over 2, which is the equation we use for kinetic energy. That's if you're interested in that. It's devised by, in the example, a motorcycle that starts at 0. The final V is constant. So anyway, that's a little bit more interest sake, just so you know that work and energy are connected. This is the important part. Or this, whatever, same thing. The work energy principle. This is how they are related. Basically, it comes down to this. This is the important part. Work is final kinetic energy minus initial kinetic energy. And this is with the formulas. Quite often, you'll have something that starts from rest. And if it's at rest, VI is 0, so this whole thing is 0, so you don't even need it if it's something starting from rest. If it ends at rest, like so if it starts at something and slows down, it's going to be negative. Watch for that. We'll do examples. We'll see this. If this is not showing up well, it should. Work sub net is mvf squared over 2 minus mvi squared over 2. Cool. Kinetic energy, we just did that. Potential energy. Take that down. Potential energy is energy at rest or stored. Think of an object about to fall off of a shelf or a stretched elastic band. It's got potential. An elastic band is the easiest one to talk about. I use that example all the time in person. All the time, like at parties. If I pull an elastic band, do I have one sitting around here somewhere? Because I know you guys can't imagine what one looks like, so I'll have to show you. Oh, beautiful. So here's this bad boy here. That has no potential energy. Outside of the fact, unless we compare this to its height off the floor, then it could fall. There's some energy there. But the elastic band on its own, the more I stretch, the more potential it has. Now, if I snap myself here just a little bit, I feel that, not a big deal. If I pull it further, there's more potential. How much of a chicken am I? Ow. Okay, and then if I go really far, then I would like pain, and I don't. So think of that. When it's pulled, it's stretched, it's potential. If you let it go, like if I shoot it through the air, as it's flying through the air, that's kinetic energy. And the slower it gets through the air as it slows down, the less kinetic energy. The energy gets lost to friction and things like that. Anyway, gravitational potential energy, we will be talking about elastic potential, just not today. Gravitational potential energy refers to the first example above or any other similar situation. With respect to gravity, we need a reference level so we can compute the potential energy. If I'm going to throw something off the roof of my house, we're taking the height of my house into account. Now, if we throw something off the roof of the gym at the school, either gym, that's a lot higher. You're going to have more potential energy. You're going to have a much higher speed right before it hits the ground. Okay? If it's just dropped. Computer's too close. Gravitational potential energy may be calculated using the equation EG, so E sub G for gravity, where EK is kinetic energy, equals mgh. Mass times gravity times height. So G is going to be the constant. It says when near the Earth's surface. That doesn't mean within a meter. That means not Mount Everest. That means not space. Okay, this is for all our purposes. We don't have to go to 9.76 or something. Height is always in meters. Mass is always in kilograms. If you get something in grams, excuse me, if you drop a penny or something, you got to convert that to kilograms. Mechanical energy is the sum of kinetic and gravitational potential. Sometimes kinetic or potential is zero. Like if I drop something, if I drop something from here, this right here, this is where, right before it hits, this is where kinetic energy is its greatest. Potential is almost zero if it's right before the ground. Gravitational here is at its greatest. It's got all this distance to fall. There's no kinetic energy. If we're just holding it, we're about to drop it. But it transfers. As this object drops, potential goes down because it's being converted to kinetic. Potential goes down, kinetic goes up as it drops. Cool, cool, cool. Something tells me there's a graph that kind of shows that, but that might be something in grade 12 when we get to other parts of this. Okay, so bleep, bleep, bleep. You can read that. You saw that. That was notes. Okay, potential and kinetic add up to get mechanical. Cool. Cool beans. Page 235, 1 to 6. I'm not going to write in marker because I'm going to use the other side of this, but I'll tell you which tutorial questions I'm doing. So there's practice on page 231. These are the easiest ones. I probably would not do these with you in class because I think they're so straightforward, but I'm going to do it now just so we don't miss anything. Also in class, because when you do it, I'm right there to answer questions. The next page is 232. Gets a wee bit trickier. This is just this right here is just 1/2 mv squared. Let's solve for energy. Let's solve for mass. Let's solve for velocity. That's it. Page 232 starts looking at how energy equals work, and 234. Was this 231? And the time I spend on dumb things. Page 234. Yeah, that's right. This is the funnest part to me. The funnest of this stuff. All right. Okay, cool. You ready to get down to business? I'm going to pause it while I set up my note-taking papers. All right. I think we're set up. I think that's clear. I'll double check once I get right in the middle of the page here. Practice numero uno. It says a 70 kilogram athlete, mass equals 70, is running at 12 meters per second. V, I don't know if it's VI, VF, let's just say V right now. V equals 12 in the 100-meter dash. What is the kinetic energy of the athlete? Okay, I wrote this down. This doesn't matter. And this is assuming that this dude is like start to go, doesn't accelerate or anything, just after the gun he's at 12. Whatever, who cares? Doesn't matter. It's just a practice example. So EK equals 1/2 mv squared. That's 1/2 times the mass, which is 70, times the velocity, which is 12 squared. 12 squared is 144, half of 70 is 35, so 144 times 35 is 5,040. 5040. If we want two sig figs, we can say 5.0 times 10 to the 3 joules, or you could say 5.0 kilojoules. I feel like I'm writing small. I'll write bigger for the next one. Okay, just plug and play. There's your formula, put the numbers in. Not always going to be that easy. Number 2, a dynamics card has a kinetic energy. It's already telling us what the kinetic energy is. Equals 4.2 joules. I need to do vocal warm-ups instead of recording first thing in the morning. The velocity, excuse me, equals 5. What is the mass of the cart? Okay, same formula. 1/2 mv squared. EK is 4.2. 1/2 the mass, which we don't know, and the velocity, though, is 5 squared. So 4.2 times 2 divided by 25 is going to give us the mass. What is this? A dynamics cart. Okay, yeah, it should be small by the looks of things. So, excuse me, 4.2 times 2. Hello. What the? 2 times 4.2 divided by, excuse me, 25 equals m. So 8.4 divided by 25 equals 0.336 or 0.34, 0.34 kilograms. Okay, I'm going to try and look at this stuff, eh? I don't like throwing anything out. I'm going to try and squeeze this in here. So number 3, still page 231. 150 gram bird. Remember when I said you got to watch for that. So this is 150 grams, which is 0.15 kilograms. Always got to be in kilograms. Kinetic energy of 30. How fast is it going? That's what it's going to say. What's the speed of the bird? V equals, so notice it says speed. It's not saying velocity. If it's saying velocity, we need a direction. It's saying speed, so we don't. And in this case, goes into a dive, we would just say down. Anyways, notice this is speed. If you give a direction, you're answering for velocity, and that is not entirely correct. It's not like you can just throw a direction on every time and be covered, okay? You need to pay attention to what the question is asking. All right, EK equals 1/2 mv squared. EK is 30 equals 1/2. The mass is 0.15 times v squared. So it's going to be 30 times 2, multiply both sides by 2, divided by 0.15. So it's going to be 60 over 0.15. I should be able to do that in my head. And then you got to take the square root of that. 60 divided by 15 is 4, 2 decimal places, so it's 400. So it's the square, so it's 20. But I should show you my steps. 30 times 2 divided by 0.15 equals, would have been this squared, or take the square root of it. Okay, so V equals 20. We want 2 sig figs, so 2, 0. You can just put a decimal there. Meters per second, or you could say 2.0 times 10 to the 1 meters per second. This seems a little bit silly, a little bit like extra work. Oh, just about didn't make the page. Cool, cool, cool. Good, good, good. I screwed up in one of my examples. I got to pay attention. I screwed up in one of my examples in pre-cal yesterday, 8C, something like that. I keep reminding myself I need to address it in the pre-cal video. All right, that was the first page of examples. Second page, page 232. A 1,300 kilogram car, right off the hop. Mass equals 1,300. Starts from rest. Oh, here we go. VI equals 0. A stoplight accelerates to a speed of 14. VF equals 14. Lost my spot. Over displacement of 82. D equals 82. So we're probably going to need acceleration. I doubt we'll need time. Calculate the net work done on the car. Okay, work is force times distance. Force is mass times acceleration. We need acceleration. I feel like I'm going a little bit fast. Work is force times distance because it's asking for the work done. Force is mass times acceleration. We don't have acceleration. Work equals mass times acceleration times displacement. We got the displacement. We got to solve for acceleration first. So I'm going to use a formula that doesn't have time. Vf squared equals Vi squared plus 2AD. Vf is 14. Vi is 0. 2 times A, and then displacement is 82. 14 squared, what is that, 196? No, 14 squared, yeah, 196. So we have 196 divided by 2 divided by 82. It's going to equal A. So 196 divided by 2 equals 98, divided by 82 is 1.195. That's our acceleration. 1.195. So now work equals mass times acceleration times displacement. We have everything we need. 1300 times 1.195. Displacement is 82. 82. I need something to drink. This times 1300 times 82. 127,400. 127,400. So how many sig figs? Probably 2. Yeah. So that equals 130,000 joules. Textbook probably says 130 kilojoules. Yep, same thing. Pause while I get water. All right. That was one number. Oh, that was 1A, sorry. Let's do 1B. I'm going to flip the page over because I'm weird like that. B says, calculate the net force acting on the car. Sorry, we did that over here. I did this question in a weird way, sorry. Force, like I solved for acceleration so I could get the net work. You know what it wanted to do. It wanted me to do. So B is just, we have the acceleration. We already did that. But I'm going to show you kind of what I maybe should have done. Work equals EKF minus EKI. This thing started from rest, so this one starts at 0. So this here is 1/2 mv squared at its final speed, which was 14. 1/2 times 1300 times 14 squared. I'll show you, it'll give you the same answer. I just went into autopilot. 196 times 1300 equals that divided by 2. Yeah, you get the same answer. I just did it a different way. Sorry about that. So notice the way I did it was a little bit longer. Clearly this is a quicker way. I guess I was stuck on the previous kind of lesson way of doing it. But it all lines up. If you're doing the right stuff with the right information, it all works out. Hopefully that makes sense. Hopefully I didn't mess with you too severely. That's probably a good thing. All right, number 2 on page 232. What does this say? 52 kilogram ice hockey player. M equals 52. Moving at 11. Oh, it's initial. VI equals 11. slows down and stops. VF, come to a stop. That means final velocity is 0. Displacement of 8. Probably going to need acceleration again. Oh, goodness gracious. Calculate the net force on the skater. So we need acceleration, then F equals ma. What was the formula? Without time, Vf squared equals Vi squared plus 2AD. Vf is 0. Vi 11. 11 squared is 121 plus 2 times D, 2 times A is 16, so plus 16A. So we subtract 121 from both sides, negative 121, and then we're going to divide both sides by 16. That'll equal A. Negative, that means something. That's there for a reason. You're thinking, wait a minute, negative acceleration? Yes, that means it's slowing down. 121 divided by 16. In case you're wondering, you'll notice, like, I rarely throw negatives in. When I'm doing something relatively simple. If it's a big multi-step thing, I'll put it in. But here, it's an added step. It's a pain to me. I just put a negative in front of that when I write it down, in case you've ever wondered. Negative 7.5625. So this bad boy's slowing down, which makes sense. Initial speed is 11, or velocity, whatever it said. Final is 0. It's slowing down, so it means a negative acceleration. This question says calculate the net force on the skater. F equals ma. Mass 52 times negative 7.5625. So this times 52, 393.25. Negative 393.25, which equals 2 sig figs, 390 newtons, and it'll be like backwards, opposing motion. Is that the short version of backwards? Yeah, it is. I just decided. That's 2A. To B, can you guys hear that squeaking and the honking and stuff? They're working on the school across the street from me on the roof. I don't think they're social distancing. All right, B says give 2 reasons why you can predict that the network, that's 2 words, not network, that the net work on the skater must be negative. 2 reasons. Slowing down. That's the first one, for sure. And when I'm saying, because the skater is skating forward, right? The direction they're going is one way, but the force is going the other. So they're slowing down. That's kind of the real life way. You could say force opposes direction, if you want to get all mathematical. Okay? Sure you have those ideas. All right. Now, like I said, I wouldn't take, what is this, some handout I got? Can I use any more paper from this? Start with that one. Probably more. I'm going to pause this while I do this. Hello and welcome back. I think what I was starting to say before I got distracted is I wouldn't take this much time in class. I'm not saying that's a bad thing or anything, but as you can see, I'm doing every single practice to make sure, everything's super clear for all y'all. Okay, page 234. If you're not looking at this, you should get the visual. I like stuff like this. So if you're looking at this, you see that this shows this kind of stair situation, that something like this. Those are stairs. And then, but right on the facing page, there's kind of a roller coaster thing. The potential energy at the top is way more than the potential energy kind of in the middle and on the ground. And you'll need to be able to calculate certain things. We're not there yet, but it's going to get to a place where you're going to be given the total mechanical energy, and then like say the height. So you'll need to be able to figure out both the potential, the MGH, and the kinetic, and so on and so forth. Anyways, first one is person walking downstairs. Mass equals 58. Walks down a flight of stairs using the ground as a reference level. Okay, A. It says calculate the person's gravitational potential energy. Remember, EG equals MGH. Calculate the person's gravitational potential energy at the top of the stairs, on the landing, and at ground level. So at 6 meters, at 3 meters, and at 0. All you're doing is punching these numbers into here. So at top, I'm going to say EG top equals, so the mass is 58. G is gravity, 9.8. The height, 6. I think you can see where this is going. 58 times 9.8 times 6. 3410 or 3400 with 2 sig figs. 3400 joules. This is at the top. This marker's really smelly. EG middle, is that what we're calling it? The landing. That looks like a 1. Okay. Handwriting L equals MGH, 58. This is the same. G, the same. The height is different now. It's only 3. So it's going to be half of this. 1700 joules. Lastly, but not leastly, maybe leastly. It will be leastly. The potential energy on the, what is it, the ground, the floor? Ground level. EGG, the egg, 58 times 9.8 times 0. That's the distance. That's the height, right? 6 meters. 6 meters from the floor. 3 meters from the floor. There's no difference, no distance, no displacement, no space. Pull out your calculator. 0. Now here's the thing. 2 sig figs, my friends. 2 sig frigs. Get into this habit. I know the textbook doesn't have it that way. I want you to get in that habit because some of you, Luke, I won't mention names, Richie, seem to think this is just optional. It's not. Okay? Get your sig figs and your units down. Okay, so that's part A. What does part C you want? B, I mean. What happens to gravitational potential energy as you go down a flight of stairs? Well, it goes down. What happens to gravitational potential energy as you climb a flight of stairs? It goes up. If you're on a roller coaster, if you've ever done one of these bad boys, this is called a clothoid loop. I don't even know how to say it. As you go up, your potential energy increases, your kinetic energy decreases. You're slowing down. You get here, your max potential, and your lowest kinetic, and then you start speeding up again because you're losing all that potential. It's converting into kinetic as it goes down. Cool, cool, cool. Same as like I'm always forever in class throwing a pen up in the air. Slows down, slows down, slows down, stops. Speeds up, speeds up, speeds up. Max potential up here, least kinetic. Right as soon as I leave it, as soon as I let it go, as soon as it leaves my hand, that's its top speed. Top speed right before it hits. All right, that's enough of me talking. Peace.